Hello everyone, welcome back. So last time we concluded our discussion of differential cryptanalysis. So we first talk about the theory behind the differential cryptanalysis, then we found differential distinguishers for the present cipher, and we experimentally verified these distinguishers. Then we use those distinguishers to attack present and capture some round keys, and we obtain the round keys during our homeworks. So we can now move on to variations of differential cryptanalysis. So in the literature there are different types of differential cryptanalysis. So we will talk a little bit about them, but our focus will be on impossible differential cryptanalysis. So after giving the main idea behind the impossible differential cryptanalysis, my aim is to talk about the height block cipher, because we can easily apply this technique for many rounds of this lightweight block cipher. So at the end, probably in a second video, I will explain how we can find a distinguisher for impossible differential distinguisher for the block cipher height, and how we can use it to attack this cipher. So let's recall that differential cryptanalysis was first publicly announced by Eli Biham and Adi Shamir in early 1980s. So I'm saying it with first public announcement because we know that NSA knew this technique as early as 1970s, because they modified the S-boxes of DES according to this, because they already knew this technique, but probably they knew it way before this date. But we also know that Japanese knew this technique even as early as in the Second World War. So many secret agencies knew this technique for years, but they kept it secret. But in an academic world, the first public announcement was by Eli Biham and Adi Shamir, and especially when Eli Biham became an IACR fellow, when he gave the talk How to Make a Difference, he thanked all of these secret agencies because they kept it secret, so that the honor would be to announce it were for Biham and Shamir. So let's recall that the idea, our aim was to find the path. Sometimes we call characteristic, sometimes we call it differential, but the aim was that when the input difference is alpha, the output difference is beta with high probability. So aim is to actually make a small change in the input and see how the small changes affect the output. So we already talked a lot about this. Later on, Knudsen modified this technique, let's say, and discovered truncated differential cryptanalysis in 1994. In this case, the idea is the same. They are trying to find the differential so that when the input difference is alpha and the output difference is beta with high probability. But this time, we are not explicitly specifying every bit difference in this alpha and beta, but we are only specifying the parts of the differences. So most of the time for notation we use question marks where the difference can be 0 or 1. So we don't care, but we are all focusing on some bits. Later on, in 1998, impossible differential cryptanalysis was discovered. Actually, this term was first used by Knudsen in his application to AES competition when he was analyzing his own cipher deal. He proposed an attack where an impossible differential technique is used. But then Biham, Birikov and Shamir generalized this idea and attacked many ciphers, including skipjack. And skipjack is an NSA design cipher, and the cipher has 32 rounds. And with this technique, Biham, Birikov and Shamir cryptanalyzed 31 rounds. So it doesn't break the whole cipher, but it breaks almost the whole cipher. Of course in a theoretical way, but not in a practical way. But this made academicians think that the NSA didn't know this technique before designing skipjack, because skipjack is really resistant to differential cryptanalysis, but not to impossible differential cryptanalysis. So in this case, the idea is somewhat different. We are trying to find a path. This time we will call it impossible differentials, so our distinguishers will be impossible differentials, so that when the input difference is alpha, the output difference is never beta. So you are trying to find something impossible. There are of course many other differential cryptanalysis variants like high order differentials, boomerang attacks, rectangle attacks, and day by day new attacks are discovered. So we have many variants of differential cryptanalysis. But our focus in this lecture is impossible differential cryptanalysis. We already mentioned that this is first discovered by Knudsen and then Bihan, Birukov and Shamir in 1998. Like differential cryptanalysis, this is a chosen plaintext attack because we are introducing differences to input, so we are actually choosing what kind of plaintext we need. Our aim is to find an R-round differential. In this case it will be impossible differential because that would hold with probability 0. So this would be our R-round distinguisher. So how can you find something impossible? So that when you give an input difference, for instance, how can you say that it will not go to this output difference after many rounds? So actually, depending on the cipher design, maybe you can come up with different techniques, but a generic technique is called miss-in-the-middle technique, and it is used in the literature for many ciphers. So idea is as follows. Find the probability 1 truncated differential. So you're saying that alpha input difference goes to beta output difference after R1 rounds of encryption with probability 1. So this is, you can use this as a probability 1 truncated differential. But then you do the reverse of this. So this time you introduce another difference, but this time you go into decryption direction. So you say that this output difference has to come from this kind of difference, so gamma, if we were to decrypt it R2 rounds, let's say. So alpha has to go beta after R1 rounds, delta has to come from gamma after R2 rounds. So this means that alpha always goes to beta, but beta and gamma contradict each other. So there is some kind of contradiction between them. For instance, let's say that least significant bit in beta is 0, and if it is 1 in gamma, then this means that they don't match. They miss in the middle. So this is where the name comes from. So this would mean that alpha would always go to beta after R1 rounds, and after R2 rounds it will go to something different than delta, because delta has to come from gamma, and gamma does not match with beta. So this is the general idea behind the miss-in-the-middle technique. So how we can use such a distinguisher as an in an attack? So idea is as follows. Since this differential does not hold, so alpha does not go to delta, when we're using it for an attack, we would add a few more rounds to the top of this alpha or delta after delta. So now if we try to capture round keys, we will observe that since this is impossible, correct key would never satisfy this differential. So you will never have input alpha difference and delta output difference when the correct key is used. So aim is to try to guess round keys and check if these differences are observed. In other words, if this distinguisher is observed. So if it is observed, then the guess key cannot be the correct one. So you eliminate it. So this is why this distinguisher works like a sieve. Any round key that satisfies this differential should be a wrong one. So this way you are eliminating the wrong ones, and at the end, if you use enough pairs, only the correct key should remain. So another picture for this miss-in-the-middle technique. So let's look at it again. So you have the alpha difference with probability 1, it goes to delta after R1 rounds, let's say, and beta has to come from gamma difference after R2 rounds, again with probability 1, and they somehow contradict each other. Again, there are some differences in delta and gamma that do not match. Again, this would mean that alpha has to go to delta, and delta has to go something else other than beta. So for this reason, alpha can never go to beta after R1 plus R2 rounds. Okay. So assume that we have such a distinguisher, and let's say that we have a pair, and we want to check actually just assume that we are trying to verify this distinguisher. So assume that delta has k many fixed bits. What does this mean? This means actually as follows. Since these are truncated differentials, assume that delta has k many fixed bits. This means that either we know they are 0 or 1s. So we know that k many bits are explicitly defined. Their differences are explicitly defined. So we know k many bits to be 0 or 1, but other bits we represent with question mark. So what is the probability of observing delta? Think about a random permutation. So you have an input with alpha difference. Assume that you put it into this black box and you look at the outputs, you XOR both of them, and if you observe delta, this would mean that this is a random permutation, not the R round of the cipher that you are trying to distinguish, because you would never be able to see delta output difference when the input difference is alpha. So, but sometimes you might be unlucky because not observing delta doesn't mean that this is the R round of the distinguisher. Maybe for a random permutation, it is also possible that when you have alpha input difference, the alpha output difference might not be delta. So what is the probability of not observing delta for a random permutation? Since you are fixing k many bits, observing those k many fixed bits has the probability 1 over 2 to the power k. In other words, 2 to the power minus k. So observing delta has this probability. So not observing it, of course, is the 1 minus this number. So if you have one pair with alpha difference, and if you don't see this delta difference, maybe this is still a random permutation, but you were unlucky because this probability is high. So what you can do is you can have many input differences, many pairs with alpha input difference, and check if any of them end up with a delta output difference. So you repeat the experiment many times. So let's say that you have c times 2 to the k pairs. So, and assume that you do not observe delta output difference for all of them. What is the probability of this? Since not observing delta for a single pair has this probability, and since we are using c times 2 to the k pairs, the probability of not observing any delta for all of these pairs is this. So if you keep the c outside and 2 to the k here, now you can use a result from calculus and say that this is approximately 1 over e to the power c, which is 1 over e to the c. So this is the probability probability of not observing delta. Okay, so if you make it very small, this will mean that after using this many pairs, if you don't observe the delta difference, you will say that, okay, this is our R round cipher. So this is how you distinguish it from a random permutation. So you might think that why this approximation is how it is obtained. So actually you can see that there's 2 to the k's here, and in our example we have replaced them with n. So when n goes to infinity, this is a known result from calculus, this goes to e to the x. So this is why we have 1 over 2 to the c here. Okay. Yeah. And minus comes from here actually. Okay, so this is how we distinguish our round of the cipher from a random permutation. Okay. And in practice actually we are using many pairs, so this 2 to the k sometimes is really huge, maybe 2 to the 100. The authors of the paper actually, Bihan, Biriko and Shamir, when first discovered this technique, they provided this approximation to avoid these huge calculations, and you can easily compute the probability here. But actually today's computers can easily compute these numbers when it is even really large, like 2 to the 128 or something. So if you want a precise probability instead of an approximation, you can omit this part and you can really calculate this probability here. Sometimes, because this is actually an overestimation. This is important because sometimes you would want to calculate what is the smallest number of pairs to perform the attack. So since this is an overestimation, it is always a good idea to calculate this precisely and obtain a smaller amount of pairs so that your data complexity would be lower than this approximation. Okay. So let's summarize and actually let's generalize how this kind of attacks work. So far we always talk about statistical attacks and talk about this. So let's read again. Statistical attacks on block ciphers make use of a property of the cipher so that an incident, in our cases characteristics differentials, occurs with different probabilities depending on whether the correct key is used or not. So when you use the distinguisher, for instance, for the statistical attacks like differential cryptanalysis and truncated differentials, our distinguisher is observed with some probability p for a wrong key when you added, of course, more runs to the distinguisher. So if your distinguisher is r runs, this means that you are attacking more than r runs so that you can talk about wrong and or correct keys. Okay, we talk about this, everything starts with the distinguisher. So this property, this differential, is observed with probability p for all of the wrong keys and probability p0 for the single correct key. And for this differential cryptanalysis and truncated differential cryptanalysis, we have p0 is larger than p. Remember that this is the thing you did in the homework, because we performed the attack and we were expecting that the correct key to get more hits because we are using many pairs, and since this probability is larger than p, when we perform the experiment with n pairs, the expected values becomes n times p0 for the correct key and n times p for the wrong keys. Since this is larger than this, we are expecting that the correct key to get higher counter. Recall what's maybe one thing to mention here is that for the differential cryptanalysis, this p0 is really larger than p. Most of the time, at least 4 times. So p0 is most of the time like larger than 4 times p. For the truncated differential, since we are using question marks, which means that we don't explicitly say some of the differences, p0 becomes very close to p. Sometimes maybe 1.5 times p. Okay, so this is one of the differences between these two techniques. So if we look at the impossible differential, now we have a distinguisher, and the correct key, under the correct key, we would never observe this differential. So probability is 0. But for the wrong key, the wrong key randomization hypothesis again applies to this situation. We assume that there is no reason for the wrong key not to satisfy this differential. So we assume that it is observed with some probability p. But since the correct key can never satisfy this differential, this is why this impossible differential works as a sieve. So there is no even need to keep counters, because if a guess key gets a hit, so its counter becomes 1, then there is no need to check this key for the other pairs, because it is obvious that that is a wrong key, so we can eliminate it. This is why this impossible differential works as a sieve. Once a key, for a pair, if a key satisfies this differential, there's no need to use any more pairs for that key, and you can simply eliminate it. So at this point another question arises. So there's a case for the attacks where p0 is larger than p, and there's also a special case where p0 is less than p, but p0 is exactly 0. So question is, can we perform an attack where again the differential is observed with different probabilities for the wrong key and the correct key, like p and p0, but in this case p0 is less than p. So if we think about in the terms of probability theory, this is of course valid. You can perform the attack because these are two different binomial distributions, and since if P0 and P has if the difference increases, then it will be easier to distinguish these two different binomial distributions. So we discovered this technique and said that this is improbable differential cryptanalysis. So in theory this is possible, but the question is how can you make it work in practice? So in other words, how can you find a differential so that the correct key satisfies this differential with less probability than for a wrong key? So, but this is not, we introduce some techniques like missing the middle technique, very similar to those, but it is possible to obtain this kind of distinguishers, and you can experimentally verify attacks where you can perform improbable differential cryptanalysis in this case. So next time I will describe what the hide block cipher and give an example how impossible differential works on this cipher.